Hi guys, welcome back to ChemOrgChem. Today we are going to explore tributyltin hydride reagent and the preparation and application. If you are new to this channel, don't forget to subscribe. Let's dive in tributyltin hydride reagent. First we see the tributyltin hydride preparation and properties. So here you see the structure of tributyltin hydride. So tin has more metallic character than silicon. Therefore, it forms stable organic compounds. Those compounds are called as stannanes. So many of tin-based compounds are commercially available. And another important point is tin atom is larger than carbon. You just to compare with carbon and tin atom. So tin atom is larger atom, therefore it forms long covalent bonds. So what is the means that long covalent bonds? If it covalent bond it's long, that means that those bonds are highly polarized. If the bonds are highly polarized, we can easily break those bonds. So for our better understanding, you just see this table. So here you see the bond as well as bond length. You just compare with carbon-carbon bond length 0.15. The same time tin-carbon bond length is 0.189 angstrom. And similarly, you just compare with carbon-hydrogen and tin-hydrogen. From this table, we can easily understand the bonds are long covalent bonds. Therefore, we can easily break by homolytically. So let's see how to prepare tributyltin hydride reagent. It's simple. When you take the tributyl tin chloride and treat with lithium aluminum hydride reducing agent, which readily produce tributyltin hydride reagent. Instead of lithium aluminum hydride, we can use sodium borohydride and also sodium cyanoborohydride. So tributyltin hydride application is huge. Here you see I tabulated 10 important applications in tributyltin hydride in organic synthesis. So anyway, today we are going to discuss only two applications. The first one is reduction of organohalides and second one is dehalogenation followed by carbon-carbon coupling. Let's see first application, reduction of organohalide. We just consider this compound. This one is one of the bromo compound. When you treat tributyltin hydride in the presence of daylight or sunlight, okay, which readily reduce this compound, which produce corresponding hydrocarbon product along with tributyltin bromide. Let's see how this reaction takes place by magnetically. When you use direct sunlight or daylight, tributyltin hydride, just now we seen that tin hydrogen bonds are weak, we can easily break. Okay, so when you use sunlight, here you see this bond homolytically cleave, which produce tributyltin radical as well as hydrogen radical. So this tributyltin radical readily abstract this bromine atom from this compound. Here you see that takes the bromine atom, then followed by the CPR bond homolytically cleavage happen to produce corresponding carbon center radical. This carbon center radical readily abstract the proton from tributyltin hydride, which result that produce hydrocarbon product along with tributyltin radical. So let's see the relative rate of abstraction of halogen by tributyltin radical. So in this series clearly tells that iodine is more reactive compared to the rest of the series. At the same time, fluorine is least reactive. In case of iodo as well as bromo compound, just direct sunlight is enough in order to proceed this reaction. However, chlorine, we need some radical initiator. That radical initiator helps to produce more concentrated tributyltin radical that will boost up the reaction. So next we move on the reactive rate of different organohalides. So this series we can somewhat correlate with radical stability. Okay, so according to this series, benzyl radical is more reactive compared to rest of the radicals. At the same time, aryl is one of the least reactive. So next we moving on cohomolysis of tributyltin hydride promoted by the radical initiator. So just now I said especially bromo compounds or iodo compounds, just direct sunlight or direct daylight is enough to produce tributyltin radical. However, in case of chlorine compound, which is least reactive, therefore we need highly concentrated tributyltin radical. Therefore, when you use AABN, here is the AABN. AABN means that bis isobutronitrile. When you use this radical initiator, that helps to produce more amount of tributyltin radical, which can boost the reactivity of especially chloro compounds. So here you see when you take AABN under heating, that readily under homolytic cleavage, here you see, so this bond cleave homolytically and similarly this bond also cleave homolytically, which produce this carbon center radical along with nitrogen gas. So this carbon center radical is electrophilic radical since this radical directly attached with electron withdrawing group. So this radical readily abstract the proton from tributyltin hydride, which produce more amount of tributyltin radical. So let's see some of the examples. So here you see this compound having bromo, fluoro as well as chlorine group. However, when you use tributyltin hydride, that selectively reduces this particular group, which result that produce corresponding compound. So this is the another example. So here you see this compound having both chlorine as well as fluorine atom. When you use tributyltin hydride, that selectively reduces this chlorine group, which produce corresponding product. Here we should note the stereochemistry of this product. This reaction retention configuration is observed. That means that when you use tributyltin hydride, that readily abstract the chlorine atom, which produce corresponding radical. Okay, that radical abstract the proton from tributyltin hydride. So therefore, that radical abstraction of proton event is so much faster compared to the radical inversion process. Therefore, here this particular reaction produce retention configuration. This is the another example. When you use 1.2 equivalent of tributyltin hydride, that reduces one of the chlorine atom to produce corresponding product. So even poly dehalogenation also possible when you use deuterated form of tributyltin hydride, which produce corresponding product. The second step, when you use potassium fluoride, that help to eliminate the tributyltin waste. So this is the another example. Here you see this iodo groups reduces into corresponding product, but here something is different. When you use trimethyl tin chloride sodium borohydride, that produce in situ trimethyl tin hydride reagent, which readily abstract this iodo group and followed by abstraction of hydrogen from trimethyl tin hydride, which result that produce this corresponding product. Let's see some more example. So this is one of the interesting example. When you use tributyltin hydride, that readily abstract this iodo group which produce corresponding carbon center radical. So here you see this three-membered ring system. This is highly strained system which readily cleave when it contains near a radical. So here you see this radical goes here, then followed by this homolytic cleavage happen in this place, which results that generation of new carbon center radical. So this radical is highly stable since phenyl group is near, then followed by abstraction of hydrogen from tributyltin hydride, which produce this corresponding product. So this is the another example when you use tributyltin hydride that selectively reduces this, which produce this corresponding product along with a rearranged product. So how this rearrangement takes place? Let's see. When it produces carbon center radical that readily rearranges into produce this corresponding radical. So this radical readily abstract the proton from tributyltin hydride, which produce this corresponding rearranged product. Halogenation followed by carbon-carbon coupling. Let's consider this example. So here you see that aliphatic halide which react with electron deficient alkene in the presence of tributyltin hydride AABN, which produce corresponding carbon-carbon coupling product. Let's see how this reaction occurred by magnetically. So initially tributyltin hydride in the presence of AABN, which produce tributyltin radical along with hydrogen radical. So this tributyltin radical readily abstract the iodine from corresponding alkyl halide starting material, which readily produce tributyltin iodide byproduct along with nucleophilic radical. That means this one is nucleophilic radical. In principle, there are two types of radicals are known. One is nucleophilic radical, another one is electrophilic radical. So here in this protocol which generate nucleophilic radical, so this nucleophilic radical react with electron deficient alkene. So here you see it react with electron deficient alkene, which produce one electrophilic radical. Okay, so this electrophilic radical never react with electron deficient alkene. So why this one is electrophilic radical? Because this radical near center having electron withdrawing group. Therefore, this radical is electrophilic radical. So this electrophilic radical never react with electron deficient alkene. Therefore, which readily abstract the proton from tributyltin hydride, which produce this corresponding product along with tributyltin radical. For the successful of dehalogenation followed by carbon-carbon coupling, we should remember these three important points. The first point is tributyltin hydride should be ordered or generated very slowly. The second point is starting material. This type of starting material should contain weak carbon X bond. That means that carbon iodo or carbon bromo bond containing substrates are highly suitable for this dehalogenation followed by carbon-carbon coupling reaction. The third important point is electron deficient alkene must be present at least 10 times higher than tributyltin hydride. So if we follow these three important points, we'll get to successful of dehalogenation followed by carbon-carbon coupling reaction. So let's see some of the important examples for this particular protocol. So here you see the first example in this compound having carbon iodo group. When you subject under this condition, here you see this one is also electron deficient alkene which react to produce this corresponding compound. Here you see the retention stereochemistry is observed. Okay, so this radical attack this alkene from the top phase, which produce this corresponding product. So this is the another example. Here also see iodo compound which react with electron deficient alkene, which produce this corresponding product, corresponding carbon-carbon coupling product. So the intermolecular carbon-carbon coupling, even asymmetric or diastereoselective synthesis also possible. Here you see in this substrate. So this particular part is called Evans chiral auxiliary. So this Evans chiral auxiliary can control the stereo induction process for this particular reaction. So when you use tributyltin hydride, which readily generate corresponding nucleophilic radical of this isopropyl iodide. So here yttrium triflate act as a Lewis acid, which readily coordinate with these two oxygen, which produce a rigid structure, since rigid structure is necessary for enantiomer induction process. Therefore, when you add this isopropyl radical by bottom phase, since the top phase is highly shielded by this group, which results that produce this product. So this is the another example. So our previous all the examples we seen that the generation of nucleophilic radical, but in this particular case we are going to generate electrophilic radical, since here you see this carbon attached with two electron withdrawing ester groups. So when you use tributyltin hydride, which readily generate this corresponding radical, so this radical is electrophilic radical. That means that should react with electron rich alkene. So here you see this one is electron rich alkene, therefore which readily react with this electron rich alkene, which produce this corresponding product. Next, we moving on intramolecular cyclization or intramolecular carbon-carbon coupling. You just consider this example. Here you see this compound having both alkene as well as CX bond in the same framework. When you use tributyltin hydride ABN condition, which produce corresponding cyclic compounds. Let's see how this reaction occurred by magnetically. When you use tributyltin hydride ABN, which generate tributyltin radical, which readily abstract the halogen atom from this starting material, which generate tributyltin halide along with carbon center radical. This carbon center radical regioselectively attack this alkene, which produce corresponding radical, then followed by abstraction of hydrogen from tributyltin hydride, which produce this corresponding cyclic compound. So here, when you use excess of tributyltin hydride, so this type of cyclization never been observed. So what about the regioselectivity? Okay, so here you see the regioselectivity trend. So 5-exo cyclization is highly favored compared to rest of the series. So now you apply this rule. Here you see 1, 2, 3, 4, 5. So this one is 5-exo cyclization. Or otherwise, you just keep in your mind the formation of small ring is always favored compared to the larger ring formation. Okay, according to this, the small ring formation is favored. Here you see, when this radical attack here, you will get 5-member ring system. At the same time, when this radical attack here, you will get the 6-membered ring system. According to our rule, small ring formation is highly favored. Therefore, we are getting 5-membered ring system. Let's see some of the example. Now you consider this example. Here you see one iodo group present in this compound as well as alkene here. When you use tributyltin hydride, you will generate a radical, so which readily undergo 5-exo cyclization, which produce this corresponding radical followed by abstraction of hydrogen from tributyltin hydride, which produce this corresponding product. So now you consider this example. This was one of the interesting example. So when you use tributyltin hydride ABN, you will get the radical from here. However, this never cyclized because this alkene having highly sterically hindered tertiary butyl group that restrict to cyclize this particular reaction. Therefore, which readily abstract the proton from tributyltin hydride, which produce corresponding reduced product. So now you take this example. So this one, when you use tributyltin hydride ABN, you will readily generate a radical from here, then followed by carbon-carbon coupling will take place. So now closely look this group present in the bottom phase, therefore the cyclization takes place by bottom phase, therefore this methyl group comes up, then followed by abstraction of proton from tributyltin hydride which generate this corresponding product. So particularly this type of cyclization is called Stark cyclization. We will discuss more in depth in our next part. So this is the another example. Now you see, when you use this mixture which readily generate this alkenyl radical. So now you see the stereochemistry of this product, I mean this intermediate. So this group present in the bottom phase while the top phase having hydroxy group. Therefore the cyclization takes place by bottom phase which produce this corresponding product. So now you take this example. So when you use this mixture, you will get the radical from here, then followed by, so this group present in the top phase, therefore the cyclization takes place by top phase, which produce this corresponding intermediate. Now you see the hydrogen present in the bottom. So after generating new carbon center radical, which readily attacks the alkyne, here you see the alkyne present in the bottom phase, therefore cyclization also takes place in the bottom phase, then followed by abstraction of proton from tributyltin hydride which generate this product. So now you closely look all these examples. The stereochemistry of the final product is dictated by the stereochemistry of already present in the starting material. Let's see some more example to solidify our knowledge on tributyltin hydride. This is one of the interesting example. When you use tributyltin chloride sodium cyanoborohydride which generate in situ tributyltin hydride, under the radiation you will get the tributyltin radical. So here you see initially Stark cyclization takes place which produce new carbon center radical. So now you see the stereochemistry of this intermediate. So this group present in the bottom phase, therefore cyclization also takes place in the bottom phase, then followed by this readily undergo intermolecular carbon-carbon coupling with this alpha beta unsaturated alkene. Now you see this bottom phase highly shielded by these groups, but top phase is somewhat free, therefore this reaction takes place in the top phase which produce this product. So let's see another example. This is also one of the interesting example when you use tributyltin hydride which readily generate the arene radical, so which readily undergo 5 exocyclization which produce new carbon center radical. So this carbon center radical which readily kick off sulfur center radical. Since sulfur center radical one of the stable radical which produce corresponding alkene product. So instead of abstraction of hydrogen from tributyltin hydride, here something is different happen since the stability of sulfur center radical. Let's see some more example. So just like our carbon hollow bond, carbon sulfur bond also homolytically cleavable when you use tributyltin hydride ABN. For better understanding, you just redraw the structure in the chair form. Now you see this carbon sulfur bond is cleavable homolytically when you use tributyltin hydride which generate corresponding carbon center radical. Now this carbon center radical readily attacks this alkene by 5 exocyclization to produce this corresponding carbon-carbon coupling product. So just like our carbon sulfur bond, carbon selenium bond also cleavable just like carbon sulfur bond when you use tributyltin hydride AIBN, which generate corresponding radical which readily undergo 5-exocyclization which produce this corresponding product. So this is the another example, just like carbon-carbon double bond, carbon-carbon triple bond, carbon double bond nitrogen addition also feasible when you use tributyltin hydride AIBN. So when you use this condition, you will get the radical here, then followed by that radical undergo 5-exocyclization which produce corresponding nitrogen center radical which readily abstract the proton from tributyltin hydride which produce this corresponding product. Let's see some more examples. You just take this example. Before moving this example, you just remember that just I already said in our previous slides, the formation of small ring is highly favored compared to the formation of larger ring system. Now you consider this example. When we use tributyltin hydride AIBN, you will get the radical here. According to our previous rule, the formation of 4-member ring system should be favored. However, in this case, the 5-membered ring system is favored to produce this corresponding radical intermediate. Since this radical is highly stable, since this radical is tertiary radical, you just imagine when you cyclize 4-member ring system, you will get the radical from this position. That radical will be a secondary radical. Therefore, tertiary radical is stable. Therefore, this intermediate is generated, then followed by abstraction of proton from tributyltin hydride, which produce this corresponding product. So now you take this example. Here you see one phenyl group fused in this position. Now you use the same reaction condition which readily undergo 4-membered ring cyclization which produce corresponding this radical. Since this radical is highly stable, since this radical will stabilize by this corresponding phenyl group. However, if you get to cyclize just like our previous case, you will get the similar type of tertiary butyl radical. When compared to these two radicals, this radical is highly stable, then followed by abstraction of proton from tributyltin hydride, which produce this corresponding product. So, and there you have it. So, tributyltin hydride, one of the versatile reagent in organic synthesis. Today, we have covered just 2 applications, such as organohalide reduction and carbon-carbon coupling reaction, along with some interesting examples. So here you see some of the practice problems. When you get the free time, you just try to work it out. So if you enjoyed this content, don't forget to like, share, and comment, and subscribe for more engaging content. Until next time, bye-bye.